The sun rises in silence, yet its presence is anything but quiet. It is a roaring furnace of charged particles and incandescent plasma, a star so luminous that it devours every detail around it. Even the planets bow to its overwhelming glare. Dust vanishes. Shadows lose their meaning. Near this celestial inferno, nothing small is meant to survive, not a wandering speck of rock, not a fragile ribbon of volatile ice, and certainly not the faintest breath of a cometary halo. Around the sun, vision itself is humbled. Telescopes avert their gaze, cameras saturate, instruments fall blind, and for that reason the region closest to the star has always been a place where mysteries pass unseen, slipping through human awareness like ghosts through fire. Yet it was precisely there in this furnace of obliterating radiance that something impossible drifted. A pale filament of motion, almost imaginary in its thinness, threading the perimeter of the solar corona. Nothing about it sought attention. It carried no blazing tail at first, no extravagant plume, no grand cosmic gesture. It was a whisper passing through a hurricane, and for a long moment no one noticed. The sun in its unbroken brilliance swallowed the intruder whole. But the object continued forward, following a trajectory older than our star, older than the planets, older than the dust that builds worlds. It was an interstellar traveller, an emissary from another system, or perhaps no system at all, merely a leftover shard from a place where suns were still forming, drifting through the interstellar dark for countless epochs. It had no allegiance to the solar system. It had no history here, and it expected no witness. But the universe has a way of letting the unexpected be seen. From 150 million kilometers away, a NASA spacecraft stared directly at the sun, not because it sought visitors from deep space, but because it was designed to study eruptions, magnetic waves, solar storms, and the physics of the star's outer atmosphere. Every frame it captured was meant to measure solar violence. Every calibration was bent toward surviving the star's glare. Such instruments were not built for comet hunting, yet one frame carried a small disturbance. A dot, a faint, barely distinguishable grain of light shifting against the fan of solar wind streaming outward. At first it meant nothing. A pixel, a minor artifact, a mote drifting through the vision of a machine. Still something about its movement disagreed with randomness. Its arc was too smooth, too consistent, too anchored in celestial geometry. It was moving not with the solar wind, but across it, defying the radial flow of particles. It was dim, impossibly dim, almost fading into the sun's surrounding brightness. And yet, despite the tyranny of glare, despite the searing noise drowning every detail, this object left a trace. It was as though the sun itself could not fully erase it. The spacecraft kept watching, the frames accumulated, and that faint point of light continued to shift slowly, deliberately, with the unmistakable signature of a genuine celestial body. There was no announcement, no sudden revelation, no fanfare. The moment passed without drama. But later, when analysts pored over the data looking for coronal mass ejections and solar wave patterns, they found something else woven into the sequence motion that did not belong to the sun at all. At that instant, the narrative of Three-Eye Atlas began, though no one yet knew its name. It was only a whisper of motion and a suggestion of path, but it carried a weight far greater than its dusty core. Because once its orbit was computed, once its speed and direction were traced backward beyond the sun, and beyond the solar system's boundaries, a realization dawned with quiet, breathtaking certainty. This was no ordinary comet. It was interstellar, a traveller from elsewhere, a visitor that had crossed the gulf between stars and had chosen by sheer coincidence to graze the most blinding region of our sky, the place where human instruments see least and where cosmic objects most easily disappear. For a moment its presence near the sun felt almost symbolic, as though two ancient entities had brushed past each other, one a steady beacon of thermonuclear fury, the other a drifting shard forged by distant cosmic chemistry. They shared nothing except a fleeting intersection in space and time. The sun did not notice this visitor, but Earth did, and so a new mystery emerged, not just the nature of this interstellar body, but the improbable fact that humanity detected it at all. How does something so faint survive against the most merciless glare in the solar system? How does an object born from another star reveal itself at the very edge of our blindness? How does a whisper rise above the roar of a star? This tension between visibility and invisibility, between cosmic coincidence, and human perception forms the heart of the mystery. NASA did not point its eyes toward the Sun, expecting to catch an interstellar wanderer. The event was not planned, it was not expected, it was not even considered likely. Interstellar objects are so rare, so fleeting, and so faint that most pass unnoticed in the vastness between stars and worlds. Yet this one three-eye atlas wandered into the worst possible observational environment, and was still seen. Something about that fact reshapes the question. The mystery becomes more than a comet's origin. It becomes a story about detection limits, about human ingenuity, and about the paradox of discovering the almost undiscoverable. It becomes a meditation on the fine line between blindness and revelation. Even now, the opening frames of its appearance feel unreal. A smudge against fire, a subtle line of motion, a quiet interstellar traveller brushing the sun's domain. It feels like an omen, a cosmic parable, about how much escapes our awareness, and how rare it is for something from beyond the solar system to declare itself, especially where the universe is brightest. And so begins the unfolding of this strange encounter between a star and a wanderer, and humanity's attempt to understand how, against all logic, the sun's overwhelming brilliance could not fully conceal an object forged in another corner of the galaxy. It began as many great discoveries do, with an accident. NASA's solar observatories were not designed to study interstellar debris. Their mission was simpler, more terrestrial in its consequences, to understand the sun's activity, its cycles of rage and rest, its eruptions that shake the magnetic architecture of Earth. They watched for flares that could disrupt communication satellites, for coronal mass ejections that might endanger astronauts, for solar wind disturbances that ripple across the magnetosphere. The goal was vigilance, not exploration. The instruments were guardians, not hunters. But great cosmic stories rarely ask permission before unfolding. The spacecraft, whose images would eventually reveal Three-Eye Atlas, was part of a lineage stretching back decades. It was a descendant of a tradition that began with SOHO, the Solar and Heliospheric Observatory, launched in the mid-1990s to monitor the Sun from the gravitational equilibrium of the L1 point. Later came stereo twin probes sent into solar orbit to give humanity stereo vision of the Sun, allowing eruptions to be triangulated in 3 dimensions. More recently, observatories like the Parker Solar Probe ventured closer, still daring to fly through the Sun's expanding outer atmosphere to taste the solar wind at its source. These instruments were trained always on the star at the centre of our system, cataloguing its moods with relentless precision. In the midst of this vigilant watching, NASA teams sifted through data streams that were as relentless as the star itself. Coronagraph images, heliospheric snapshots, ultraviolet bursts, plasma spectra, every second brought new information. Human eyes could not possibly scan it all. Algorithms flagged solar events. Analysts reviewed anomalies. The Sun offered no shortage of phenomena to study. And then, buried inside one sequence, something moved that did not belong. It was subtle, so subtle that early analysts dismissed it as a fragment of noise, a camera artifact born from scattered light or sensor heating. Near the Sun, such artifacts are common. Even high-grade electronics strain under the constant assault of radiation. Pixels flicker, light scatters unpredictably, glints appear where none should exist. In such an environment, faint moving points are easy to ignore. They come and go without meaning. The first person to notice the anomaly was not searching for anything unusual. They were reviewing a time-lapse sequence from a wide-field solar imager that monitored the outer heliosphere for large-scale solar wind structures. The frames revealed a steady outward flow of charged particles, a solar breeze glowing faintly against the emptiness. But in one corner of the field, something drifted sideways. It was too slow to be debris from the spacecraft, too steady to be sensor noise, too consistent in brightness to be an isolated camera artifact. And importantly, it appeared in more than one frame. That was enough to raise curiosity. The analyst flagged the sequence. A second observer reviewed it and confirmed the anomaly. Coordinates were estimated. The apparent motion was measured. With each check, the object grew less deniable. It left a trail faint but coherent through the blinding field of solar light. Still, no one suspected an interstellar visitor. That idea was almost unthinkable. Just a few years earlier, the discovery of the first known interstellar object, One-Eye Oumuamua, had shaken the scientific world. Its unusual shape, its non-gravitational acceleration, its silent passing had sparked debates from icy debris to exotic technology. After that, the comet 2I Borisov arrived more conventional in behaviour yet equally profound. Two interstellar objects in such a short window had left astronomers uncertain were they common after all, or was humanity simply becoming better at noticing them? Even with that memory still fresh in scientific discussion, analysts reviewing solar data did not leap to conclusions. Strange comets graze the sun all the time. Thousands have been spotted in the past plunging inward on long looping orbits that carry them perilously close to the star. Many disintegrate, some survive. Almost all are captured by solar observatories that constantly watch for near-sun comets, belonging to families like the Kreutz sungrazers. The working assumption was simple: this was probably one more, and yet something about its path felt wrong. When initial estimates of its trajectory were produced rough preliminary full of uncertainty, they did not resemble the looping arcs of periodic comets. Instead, the numbers hinted at a shape too open, too steep, too unbound. It looked less like an ellipse, and more like a hyperbola, a geometry that implies freedom, not captivity. A hyperbolic path spoke of an object that would not return. But hyperbolic does not always mean interstellar. Close encounters with planets can sling comets onto such paths. Gravitational interactions can accelerate them. Appearances deceive. The team needed more data. They searched for earlier frames, older sequences, adjacent observations. Bit by bit, they pieced together a longer track. And with every additional point, the truth grew harder to ignore. The object was indeed following a hyperbolic trajectory, and its incoming direction when projected far enough backward did not intersect the orbits of the giant planets. It intersected nothing. Its path led from deep space. Only then did the memory of Oumuamua whisper through the minds of the analysts. Only then did Borisov's name return like a quiet echo. For the first time, a possibility emerged that felt both extraordinary and unnerving. Could this faint object, barely visible against the solar blaze, be the third known interstellar visitor? To test the hypothesis, scientists turned to ATLAS, the Asteroid Terrestrial Impact Last Alert System, a sky survey program designed to spot hazardous near-Earth objects. ATLAS had recorded pre-discovery images of comets before. It was the sort of wide-field observer that could catch a faint object long before it neared the sun. When ATLAS images were checked, a new trail was waiting. Dim, almost imperceptible, but unmistakably present. The Wide-Field Sky Survey had indeed captured the comet earlier prior to its near-solar approach, and alongside NASA's solar data, these observations now formed the foundation of a more precise orbital reconstruction. The verdict crystallized quickly. This was not a solar system comet. It was not born in the Kuiper Belt, not from the Oort cloud, not from any frozen reservoir orbiting our star. It had travelled from the space between stars, a fragment of another system drifting across the galaxy, until by pure coincidence the solar system crossed its path. Only by passing near the sun, only by wandering into a domain filled with instruments trained to detect solar storms did 3I Atlas become visible at all. Its discovery was a moment of rare scientific serendipity. Humans watching the sun focused on a star's ferocity, accidentally glimpsing a traveller from beyond the sun's realm. And that sudden overlap between a star's unyielding brilliance and a wanderer's dim passage opened a new frontier of questions about what else might be drifting invisibly through the interstellar dark. In the end, the discovery of 3I Atlas was less an act of purposeful search, and more a cosmic coincidence, the right object at the right moment, passing through the only place in the solar system where instruments continuously stare. It was a reminder that sometimes the universe reveals its secrets not through intention, but through the quiet intersection of curiosity, persistence, and chance, allowing humanity to witness something it was never truly looking for. The moment the anomaly's motion was confirmed, analysts began peeling back the layers of its identity, and with each calculation the object resisted belonging to anything familiar. Ordinary comets announce themselves through predictable patterns. They glide along elliptical paths tethered to the sun by ancient gravitational bindings. Their arcs return in cycles that span decades, centuries, or millennia. Even new long-period comets obey the geometry of a system shaped by a single star's pull. But the faint traveller emerging in NASA's solar data did not bend gently toward the sun as a native comet would. It fell sharply, almost straight, as though gravity merely nudged it rather than claimed it. That motion alone evoked suspicion. When orbital reconstruction began in earnest, astronomers turned to a standard method fitting observed positions against models of Keplerian trajectories. Solar system comets almost always settle into elliptic solutions looping back toward a distant aphelion, that lies somewhere within the gravitational reach of the Sun. The numbers here, however, refuse to settle. The best fit curve consistently pushed toward Ejection. 1. Eccentricity greater than 1 indicating a hyperbolic orbit. Hyperbolic orbits are the signatures of escape of objects moving too fast to be bound. But still caution persisted. Some comets appear hyperbolic due to observational error. Others become hyperbolic after interacting with Jupiter-Saturn, or even passing stars. Planetary encounters can steal or grant energy, tilting a comet's path from closed to open. So the next question became one of origins. Could this object have been slingshotted by one of the giant planets? Planetary backtracking simulations quickly answered that. When its trajectory was projected backward through time, days, weeks, then months, it never came close to a planet large enough to fling it onto such a path. The gas giants remained distant by millions of kilometers. Nothing in the solar system had touched it. And then came the directionality test, the same technique used on Oumuamua and Borisov. Astronomers examined the object's radiant the incoming direction from which it approached, projected beyond the solar system's boundary. If it belonged to humanity's home star, the radiant would trace back to the Oort cloud the enormous spherical reservoir of icy debris surrounding the Sun at the system's edge. But this object's radiant pointed nowhere near that ancient shell. It pointed into interstellar space. The realization washed through the research team in a quiet ripple. Those involved remembered the astonishment that followed the discovery of Oumuamua, the first known visitor from beyond the solar system. They recalled the excitement and debates around Borisov, a comet that behaved more like familiar solar system objects, yet carried a chemical signature that hinted at its alien birth. But here once again was something foreign, something older than the planets, and older than the Sun. The designation 3I, the third known interstellar object, had not yet been assigned, but its identity was becoming unmistakable. As the data accumulated, more telescopes joined the effort. Though the object was faint, ground-based observatories benefited from knowing precisely where to look, thanks to NASA's solar images and pre-discovery records from Atlas. Each new measurement sharpened the orbit further, stripping away ambiguity, until its hyperbolic excess velocity became clear as speed too high for solar origin, too steady for gravitational scattering, too cold and ancient for anything but the journey between stars. This was Unmasking, a slow, methodical peeling back of the Sun's blinding camouflage. But the strangest part of the story was not its interstellar nature. The cosmos may be filled with such travellers, fragments of distant planetary systems cast adrift during epochs of formation or destruction. They wander the galaxy endlessly, rarely encountering stars and even more rarely passing close enough to be seen. What made 3I Atlas extraordinary was the sheer improbability of detecting it in the one place where comets are hardest to observe against the Sun. A faint body drifting through the glare of the solar corona is something almost guaranteed to escape human vision. Solar telescopes are not designed to detect objects of such faintness. The glare saturates sensors. The dynamic range collapses. Low contrast features disappear. Yet somehow the comet left a detectable signature, just enough brightness, just enough persistence, just enough movement to stand apart from noise. The Sun in all its ferocity could not erase it completely. To understand how astonishing that is, one must consider the environment near the Sun. A comet approaching the star is subject to extreme thermal stress. Ice sublimates violently. Dust streams outward in chaotic jets. Radiation pressure buffets loose particles, distorting the tail. The nucleus fractures under tidal forces and heat gradients. And yet at the time of detection, 3I Atlas exhibited only a modest brightening, barely enough to register. In that sense, the object behaved more like Oumuamua than Borisov. Borisov had produced a classic bright cometary coma, almost immediately spilling dust and gas in a familiar display. Oumuamua had shown no such behaviour, remaining unexpectedly quiet like a shard of rock or compacted ice with minimal volatile content. 3I Atlas fell somewhere between the two. It produced some sublimation, but not enough to blaze through the Sun's overwhelming luminance. It revealed just a faint envelope thin as a breath that stretched behind it in a ghostly line. Even that hint was enough. Small differences in brightness can mean the difference between discovery and oblivion. Had 3I Atlas been slightly dimmer, or had the timing of NASA's solar imaging differed by mere minutes, it might have slipped through unnoticed. Interstellar visitors may be common, but their detection is finely tuned to the balance of chance. They are glimpsed only when the cosmos allows it. Once unmasked, the object became a subject of quiet fascination. Its photometric behaviour hinted at an icy composition, but the rate of brightening seemed inconsistent with typical solar system comets. The shape of its coma appeared asymmetric, suggesting unusual internal structure or rotational activity. These features hinted at a long solitary existence in the vacuum between stars, an existence that strips of volatile layers, hardens the nucleus, and leaves behind only pockets of ice preserved deep within. This evolutionary path is distinct from that of the comets that orbit our Sun. Solar system comets undergo periodic heating every time they approach the star, even if the cycle spans tens of thousands of years. Such heating shapes their composition, alters their surfaces, and removes their more fragile materials early in their lifetime. Interstellar comets, by contrast, spend billions of years drifting through cold darkness, untouched and unmodified by stellar warmth. They age in silence. The unmasking of 3i Atlas therefore represented more than identifying an orbit. It was a glimpse into a physical history that predates the solar system, a relic of cosmic processes occurring in distant stellar nurseries, perhaps from a system long dissolved, perhaps from a star still shining, or perhaps from a place so far away that the identity of its birthplace may never be known. And yet such speculation arises only after the fundamental truth is accepted, that against all odds a piece of interstellar matter wandered into the Sun's furnace and allowed itself to be seen. The strangeness of the object's origin became clear not through a dramatic revelation, but through the careful accumulation of small details, the curvature of its path, the persistence of its faint glow, the alignment of its radiant, the resistance of its motion to solar system explanations. This was unmasking in the scientific sense, a gradual unveiling, a slow exposure of identity through the patient work of observation and analysis. By the time astronomers formally recognized its nature, 3i Atlas had already begun to leave the Sun behind. But its fleeting appearance near the star had revealed enough to classify it as an interstellar visitor, one more messenger from the unknown passing through the most brilliant and hostile arena of the solar system. Its discovery posed a question that would echo long after the comet faded. How many other interstellar travellers slip past us unseen? How many wander across the solar system's brightest and darkest regions without detection? And how many stories like that of 3i Atlas remain hidden in places where human instruments rarely dare to look? In unmasking this faint visitor, humanity glimpsed not only an object but a deeper truth. Our cosmic neighbourhood may be far richer in interstellar wanderers than we ever imagined, yet so few announce themselves and fewer still choose to pass through the glare of a star. To understand why the discovery of 3i Atlas bordered on the improbable one, must first confront the stark reality of observing anything near the Sun. In the deep night sky, faint objects reveal themselves willingly. Stars shimmer against darkness. Comets bloom into fragile halos of dust, their tails unfurling across black expanses. Telescopes flourish there where contrast is abundant and interference is minimal. But in the vicinity of the Sun, even tens of degrees away, the universe vanishes. Light overwhelms everything. Shadows dissolve, and objects become phantoms struggling against a brilliance that does not permit the existence of subtlety. Seeing near the Sun is an act of defiance against nature. The Sun is not merely a light source, it is an instrument crusher. Its photons strike detectors with such intensity that even hardened electronics saturate instantly. Charge builds up in pixels faster than it can be drained. Scattering inside optical systems creates halos of glare, blooming glare patterns and streaks that swallow any dim structure attempting to coexist within the frame. Optical coatings struggle, filters strain, and still the star burns through. This creates a paradox. The region close to the Sun is one of the most dynamic and scientifically rich environments in the solar system. Comets plunge inward. Solar storms erupt. Magnetic field lines writhe in arcs of plasma. Fragments of distant worlds disintegrate under tidal pressure, and yet most of this unfolding drama occurs in a visual regime that resists scrutiny. Only extreme specialized instruments dare to operate there. The human eye cannot. Ground-based telescopes cannot. Even most space telescopes avert their gaze. The Sun requires its own category of instruments engineered not for delicate starlight, but for the overwhelming violence of a star's radiance. Coronagraphs are one such invention, devices that artificially eclipse the Sun placing an occulting disk inside the telescope to create an artificial night sky around the star. Yet coronagraphs suffer their own limitations. They block only the innermost light but cannot eliminate all scattering, and they reduce the field of view in ways that complicate the tracking of objects passing rapidly near the Sun. Three-Eye Atlas, as fate would have it, entered a realm that even coronagraphs find challenging too far from the occulting disk to be fully shielded yet too close to avoid the glare that floods the sensor. Detecting anything in this region requires more than simple imaging. It demands temporal analysis, watching how patterns shift over minutes, searching for coherent motion in a sea of noise, and it demands an understanding of how the Sun's own dynamic behavior introduces confusion. Solar wind structures ripple across the field like storm clouds. Coronal mass ejections erupt with sudden bursts of brightness that mimic movement. Streamers shocks and density waves scatter sunlight unpredictably. These features move, evolve and distort in ways that can easily overwhelm the faint drift of a small icy traveller. Against such chaos, a comet is nearly invisible. Adding to the difficulty is the fact that faint comets are not simple point sources. Their brightness fluctuates. Their dust envelopes change shape. Sublimation creates jets that alter their appearance unpredictably from frame to frame. Near the Sun, these effects are amplified sometimes dramatically. A small nucleus may brighten by a factor of 10 within hours, or it may dim abruptly as its volatile layers collapse. A thin tail can be twisted by radiation pressure, distorted by solar wind, or even torn away entirely. Such erratic behavior means that searching for a comet in this region is not like tracking an asteroid in a stable orbit. It is more like trying to recognize a candle flame in a storm, while sunlight fills the horizon. Astronomers have long relied on solar observatories to detect so-called sun-grazing comets, members of comet families that approach the Sun so closely that they often disintegrate. The Kreutz family alone has contributed thousands of such comets, most of them tiny, faint and fleeting. Their detection depends on motion rather than brightness. Small dots drifting across a bright background captured almost incidentally by instruments that were never intended to find them. Three-Eye Atlas mimicked this behavior, adding to the challenge. It presented itself initially as a faint moving point indistinguishable from a small sungrazer. Only through careful measurement did its track reveal unusual curvature. To appreciate the difficulty of this detection, consider the problem of dynamic range. A comet might reflect sunlight at levels thousands or millions of times fainter than the solar corona. The detector must accommodate both extremes within a single exposure. That means either the comet is at the threshold of detection barely above noise, while the surrounding solar brightness saturates, or the exposure is reduced to prevent saturation, causing the comet to vanish entirely. NASA engineers fight this battle constantly. Cameras aboard missions like SOHO Stereo and the Parker Solar Probe operate with careful exposure control, optimized not for faint comets, but for capturing the structure of solar outflows. Their detectors are adaptive, yet the brightness of the Sun often leaves only a razor-thin margin for faint object detection. In the case of Three-Eye Atlas, the margin held. The object's brightness was likely amplified slightly by sublimation, just enough to push it above detection thresholds. But it remained dim, barely more than a faint echo against the radiance. What saved it was its motion. In still frames, it would have blended into the background. In time-lapse, it traced a coherent path. Motion is the language of recognition in regions of blinding light. Analysts exploit this by stacking images, subtracting static features, enhancing moving points, and referencing past and future frames to locate consistency. This kind of temporal filtering allowed the faint interstellar object to stand out, just enough to prompt curiosity. Yet even once seen, confirming its identity required addressing another observational challenge: parallax. Solar imagers aboard different spacecraft such as Stereo A and SOHO view the Sun from different angles, creating the possibility of triangulation. But aligning observations across platforms requires precise timing, calibration of pointing errors, and accounting for spacecraft movement. For objects as faint as Three-Eye Atlas, these calibrations must be flawless. A small error in position measurement can drastically distort orbital reconstruction. For typical sun-grazing comets, such uncertainty does not matter. They are bound to the Sun regardless. But for an object suspected of interstellar origin, orbital precision must be uncompromising. The difference between a highly eccentric solar orbit and a hyperbolic interstellar trajectory may hinge on tenths of arcseconds. In other words, one pixel may decide the object's cosmic identity. Compounding the difficulty is the presence of instrumental artifacts. Cosmic rays striking detectors create false point sources. Scattering from the spacecraft structure introduces flares. Thermal noise fluctuates as the craft experiences temperature shifts. Distinguishing a faint comet from one of these artifacts requires meticulous comparison across multiple frames, and ideally across multiple instruments. NASA analysts performed these comparisons repeatedly. Frame by frame, they tracked the object. Each position was measured against the predictions of preliminary orbital solutions. Consistency emerged slowly, like a shape forming behind fog, and when ground-based Atlas observations were folded in, a new level of clarity rose from the glare. The hyperbolic path became undeniable. The faint traveller near the Sun was no native. It had come from the emptiness between stars. In that sense, the difficulty of seeing near the Sun did more than hinder detection. It amplified the significance of what survived the glare. For an object to appear at all in this hostile arena, it must be positioned perfectly illuminated just enough, and caught at the precise moment when instruments are looking. The challenge of seeing near the Sun is not merely technical, it is philosophical. It reminds humanity that many cosmic visitors pass through unseen. It reveals how narrow our observational window is, and it hints at a universe filled with wanderers that slip past our awareness, visible only when the alignment of technology, timing, and chance allows. 3i Atlas emerged from that perfect intersection, a faint signature pulled from the jaws of blindness. In its detection lies a humbling truth: our instruments, powerful though they are, reveal only a sliver of the cosmos. And yet within that sliver a shard from another star managed to leave its mark. Before astronomers could fully grasp the significance of the faint intruder drifting across the Sun's blinding halo, they needed to understand precisely which instruments had captured it, and why those instruments, designed for a completely different purpose, had nevertheless managed to reveal a visitor from beyond the solar system. The story of 3i Atlas is not only a narrative about interstellar debris brushing past a star, it is also a demonstration of how humanity's tools for studying extreme environments can occasionally illuminate mysteries that lie far beyond their intended reach. Solar observatories must perform a kind of technological alchemy. They must stare directly into a furnace without being consumed. They must measure brightness levels that span orders of magnitude. They must survive radiation storms, temperature swings, and perpetual exposure to the most unforgiving radiance in the solar system. And yet these instruments, coronagraphs, heliospheric imagers, ultraviolet telescopes, and in-situ particle detectors, form a latticework of awareness surrounding the Sun and monitoring its behaviour with unwavering vigilance. It is within this network that 3i Atlas revealed itself, recognised not because it was bright, but because the tools meant to observe solar violence inadvertently excel at detecting small moving anomalies against turbulent backgrounds. The most crucial instrument in this story was the coronagraph. A coronagraph is at its core a method for creating artificial night. The concept is elegant place an occulting disk inside the telescope to block the Sun's overwhelming photosphere, much like a perfectly aligned eclipse, and the faint corona, the Sun's outer atmosphere, becomes visible. But real coronagraphs are engineering marvels. Every stray photon must be managed, every internal reflection must be suppressed. Optical baffles, filters, and specialized coatings all work in harmony to ensure that only the tenuous ghostly glow of the corona reaches the detector. Instruments like Soho's LASCO large angle and spectrometric coronagraph have been doing this for decades. They have revealed countless sun-grazing comets, tracked solar storms, and transformed our understanding of heliophysics. But coronagraphs were never meant to detect interstellar objects. Their mission is solar, not cosmic. Their calibration is tuned to plasma waves and magnetic structures, not faint cometary dust. Yet in practice, coronagraphs observe a wide field around the Sun far larger than the occulted disk itself. This wide field is precisely what allowed 3i Atlas to be visible. As the object drifted into the region where the star's light could be sufficiently masked, the coronagraph's sensitivity to moving points became the key to detection. Still, even coronagraphs struggle against the inner corona's brightness. The fact that the object appeared at all means its sublimation had begun to intensify, producing a dust envelope bright enough to rise above the glare. Alongside the coronagraphs were heliospheric imagers, wide-angle instruments designed to track structures in the solar wind. These imagers capture immense swathes of space, revealing the motion of plasma clouds as they propagate outward. Their sensitivity is tuned differently. They observe faint brightness patterns caused by sunlight scattering off electrons in the solar wind, a phenomenon known as Thomson scattering. Because these imagers must detect faint signals spread over enormous distances, they naturally amplify subtle variations in brightness, variations that can include a dim interstellar comet, but heliospheric images add another complexity distortion. The sun's outflowing wind creates dynamic, billowing structures that constantly modulate the optical environment. To detect a moving object within this turbulence, the imagers must operate with exquisite stability, capturing snapshots at regular intervals, allowing analysts to subtract patterns, filter noise, and isolate true motion. When 3i Atlas drifted into one such image, it became a faint diagonal thread moving at odds with the outward flow, a contradiction that drew human attention. Against the background of expanding solar wind, it marched laterally, defying the radial symmetry that defines all solar structures. It was in that defiance that its identity began to whisper. Other instruments contributed as well. Some provided thermal data, revealing changes in dust flux as the comet neared the sun. Others monitored the behavior of dust particles in the solar atmosphere, indirectly highlighting changes in brightness near the object's location. Together they formed a composite vision that no single device could offer. If one were to trace the history of these tools, the detection becomes even more remarkable. NASA's solar observatories were constructed for reasons rooted in Earth's vulnerability. Solar storms can cripple power grids, disrupt navigation, and endanger astronauts. Mission planners needed eyes capable of predicting these events. They built systems resilient to heat radiation and magnetic storms instruments that could operate continuously for years or decades without faltering. These same systems turned out to be unexpectedly powerful comet watchers. SOHO alone has discovered thousands of comets, most of them tiny fragments that evaporate upon approach. But nearly all belong to families of solar system comets, each with well-understood orbits. In contrast, 3i Atlas was neither expected nor typical. Neither a familiar sun grazer nor a classically periodic visitor, it entered the solar imaging field bearing none of the characteristics astronomers anticipate. Its nucleus lacked the brightness expected of a large sun grazer. Its coma remained thin, its dust production was modest, and yet it remained visible just barely to the same instruments that capture solar plasma. Much of that visibility came down to design choices. Coronagraphs routinely balance exposures to retain faint details. Heliospheric imagers monitor large temporal windows, enabling streak detection. Spacecraft pointing remained stable for hours at a time. These factors combined into a perfect environment for finding faint, rapidly moving anomalies. But perhaps the most surprising aspect is that solar instruments, though engineered for extreme environments, possess sensitivity comparable to deep sky telescopes, at least within specific brightness regimes. Their detectors must capture faint coronal features millions of times dimmer than the sun. This inherent capability translates remarkably well into detecting faint comets. Still, the tools alone do not guarantee discovery. Detection required meticulous human attention. Analysts reviewing solar data often sift through countless hours of imagery, spotting small inconsistencies or movement patterns that algorithms misclassify. Geographic and temporal coincidences, objects drifting at particular angles, entering near specific detector regions, or passing through the field on days with minimal solar activity, can drastically improve the chances of a successful detection. 3i Atlas benefited from many such coincidences. Its passage occurred during a period of moderate solar behavior when coronal structures were relatively stable. Its position in the field aligned with an area where diffraction patterns were minimal. Its speed across the frame was low enough to be trackable, but fast enough to distinguish from dust or cosmic rays. Even the orientation of the spacecraft at the time helped reduce glare in the section of the image where the object appeared. Had any of these conditions differed, the interstellar comet might have slid invisibly through the blaze, lost forever in the sun's omnipresent light. The story of the instruments that revealed 3i Atlas is therefore also a story of thresholds. Thresholds in sensitivity, in image stability, in timing, in ambient solar conditions. It illustrates the delicate balance required to see something that should by all rights remain unseen. In a broader sense, it is a testament to the evolution of space-based solar instrumentation. Every improvement, better detectors, improved optics, enhanced calibration, has expanded humanity's observational window, not only for solar physics, but for unexpected cosmic phenomena. The tools built to study our star have become accidental archivists of interstellar wanderers. 3i Atlas passed near the sun at precisely the moment when the right instruments were watching and the right people noticed. It threaded the needle of detectability, slipping into view in a place where most objects surrender to blindness. And so in the glow of instruments forged for extremes, a faint traveller was captured, its image preserved in hardware that was never designed to see it, yet uniquely suited to unveiling it. In the quiet brilliance of that moment, the boundaries between solar science and cosmic discovery dissolved, revealing a deeper truth: the universe offers its mysteries to those who look long enough, deeply enough, and with tools resilient enough to withstand the fire of a star. Before the faint visitor was given a name, before its interstellar nature became a matter of consensus, the data began whispering something unsettling. A comet drifting through the glare of the solar corona is unlikely to behave in predictable ways. Its brightness may fluctuate, its dust may billow, its nucleus may fracture. But none of this explains the deeper shock that emerged once analysts extended the object's orbital reconstruction. The measurements pointed to a trajectory so steep, so open, that it resisted being pulled into the familiar curvature of solar system dynamics. At first the numbers seemed like a mistake. The early orbital solutions, fed by incomplete positional data from NASA's solar imagers and pre-discovery Atlas observations, refused to settle into an ellipse. Instead, the eccentricity climbed above unity, a swarm 1, indicating a hyperbolic orbit. Hyperbolic orbits are not common within the solar system. They appear under special circumstances when a comet is gravitationally flung outward by a giant planet, or when an object originates beyond the Sun's gravitational sphere of influence. The former scenario can mimic interstellar behaviour, but only if the object has recently encountered Jupiter or Saturn. Yet 3i Atlas showed no such encounter. Backward projections placed it far from the gravitational reach of any planet. The orbital backward integration was clean, undisturbed, almost eerily smooth. Nothing in our planetary system had touched it. No known body had perturbed it. The hyperbolic excess velocity, the speed with which it approached the Sun, even when accounting for solar gravity, was simply too high. This excess velocity is the signature of interstellar origin. Oumuamua had it. Borisov had it. And now this faint, quiet object carried the same unmistakable mathematical fingerprint. But the shock went deeper than merely confirming interstellar identity. It was the steepness of the trajectory that unseated expectations. The comet approached on a path that pierced the inner solar system sharply, nearly radial, compared to the broad, sweeping ellipses of most comets. This inward plunge meant that from Earth's vantage the motion was extremely difficult to track. Small positional errors dramatically altered the orbital solution, and yet every refined measurement only reinforced the same conclusion: the object was moving too fast, too straight, too free. No one wanted to admit the possibility right away. Interstellar visitors were supposed to be rare, so rare that before the arrival of One-Eye Oumuamua, none had ever been detected. Then, unexpectedly, Tuzi Borisov arrived just 2 years later. The scientific world was still processing that second event when a third appeared near the Sun, almost unnoticed, almost lost. If interstellar debris were truly this frequent, then humanity's understanding of the galaxy's dynamics would need revision. But the most destabilizing part was this: the comet had passed so close to the Sun that its detection was nearly impossible. Had its perihelion been slightly different, just a few degrees away from the solar instrument's field of view, or a few hours earlier or later, the object might have slipped through unseen. This implied that other interstellar objects, perhaps many of them, could already have visited the solar system, without leaving evidence. The shock was not simply that 3i Atlas existed. The shock was that it had been seen at all. As orbital refinement continued, another layer of strangeness emerged. Its inbound direction appeared uncorrelated with known stellar streams or motion groups. Oumuamua had arrived from the direction of the constellation Lyra near the solar apex, the direction of the Sun's movement through the galaxy. Borisov had come from the direction of Cassiopeia, consistent with a long cold drift among the stars. But 3i Atlas seemed to wander in from an unexpected vector. Its radiant did not match the distribution predicted by galactic models of interstellar object flux. It was in a sense a cosmic outlier. Such outliers provoke uncomfortable questions. Is our galaxy filled with rogue debris travelling along chaotic paths shaped by the complex gravitational tides of stellar clusters? Could the object have been flung from a young star system in turmoil? Could it be a remnant of a planetary destruction event, an icy shard stripped from the outskirts of a system that no longer exists? Speculation began to stretch beyond typical models because the trajectory did not fit neatly into them. But the shock did not end at its orbit. Its brightness pattern near perihelion also diverged from expectation. Interstellar comets, having spent billions of years in cold interstellar space, should contain volatile ices that vaporize explosively when approaching a star. Indeed, Borisov had behaved this way, shedding gas at rates suggesting an unprocessed primordial chemistry. Yet 3I Atlas brightened only modestly. Its coma remained tenuous. Its dust emission seemed weak, almost conservative, despite the fierce heat of the sun. This subdued behaviour implied one of two possibilities, each unsettling. Either the comet's surface had been hardened by eons of cosmic irradiation, sealing its volatiles beneath an insulating crust, or its composition was drastically different from typical comets, perhaps richer in refractory materials or containing exotic ices that sublimated at different thresholds. Both scenarios stretched scientific assumptions. Then came the question of structural evolution. As the comet neared the Sun, it displayed changes in morphology that refused to follow the usual patterns. Its coma shape distorted strangely. Its tail appeared segmented, suggesting intermittent bursts of activity rather than steady sublimation. These irregularities hinted at internal structures that responded violently but unpredictably to thermal stress. Could this be the imprint of an origin in a radically different environment, perhaps around a metal-poor star or a binary system, or even a star cluster with intense radiation fields? Each new anomaly deepened the shock, and all of this unfolded while the object skirted the edge of instrumental blindness barely visible behind the solar blaze. But the most paradigm-challenging data emerged when astronomers calculated what the trajectory implied about the object's history. Its hyperbolic excess speed combined with its direction suggested that it had drifted through interstellar space for an extraordinary length of time, possibly hundreds of millions of years, possibly billions. If so, the object had likely crossed near multiple stars, experienced weak gravitational nudges, survived collisions with interstellar dust, endured cosmic rays, and weathered exposure in the coldest darkness known. The comet became not just an interstellar visitor, but an interstellar survivor, and this fact reshaped scientific expectations once again. For decades, models predicted that most interstellar objects would erode into nothing during such long journeys, reduced to dust by micrometeoroid collisions or shattered by cosmic radiation. Yet here was proof that some endure long enough to reach new star systems. This realization struck a chord: the galaxy may be exchanging material far more often than previously imagined. Planetary systems may not be isolated, but part of a vast network of wandering debris, trading icy fragments like messages drifting between stars. 3I Atlas was one such message, and its detection near the Sun, a place where nothing faint should be seen, was a reminder that the universe still has the power to overturn assumptions in the quietest, most understated ways. The scientific shock then was not a single revelation but a sequence of them: the hyperbolic orbit, the unexpected radiant, the muted sublimation, the structural anomalies, the improbable survival. Together they created a portrait of an object that violated comfortable expectations about both interstellar comets and solar system detectability. The faint traveller had come from the dark between stars, but by brushing the fire of our sun it had ignited a new set of questions that now demanded deeper investigation. By the time orbital calculations confirmed that the faint traveller near the Sun was neither bound to the solar system nor sculpted by any of its planets, attention turned toward the substance of the object itself, its chemistry, its physical structure, and the long, cold evolutionary arc that shaped it before it ever met our star. The question hung quietly over every observation: what is a comet born in another system made of humanity, had tasted fragments of typical comets, icy porous bodies built from the primordial gas and dust of the early solar system? But an interstellar comet carries a different history entirely. It is chemistry forged beneath an alien sun, moulded by conditions that may never have existed here. It is a relic of a formation environment that cannot be replicated in laboratories, except in narrow fragments of approximation. For 3I Atlas, the clues began with its subtle glow. Brightness is the comet's first language. How much light it reflects, how much gas it emits, how dust spreads through its coma, these behaviours encode information about composition. Yet near the Sun, brightness is distorted by glare, solar wind, and instrument noise. Even so, the object's photometric profile contained a quiet, persistent message. Its ices behave differently from the ices of the most solar system comets. Typical comets brighten steeply as they approach the Sun. Volatiles like water, carbon dioxide, and carbon monoxide sublimate, at predictable distances, causing a rise in brightness that follows mathematical relationships long familiar to astronomers. But 3I Atlas did not follow those curves. Its brightening was muted, delayed, uneven. It did not flare in the way new comets often do. Instead, its coma thickened slowly as though its volatiles were trapped beneath a hardened crust or embedded deep inside a matrix resistant to early sublimation. This is consistent with extreme cosmic aging. A comet drifting through interstellar space for hundreds of millions of years would endure continuous exposure to ultraviolet radiation and cosmic particles. These interactions transform simple ices into complex organic materials, tar-like substances that darken and harden the surface. Beneath this irradiated shell, the original ices survive in pockets, insulated until a star's heat penetrates deeply enough to activate them. The result is delayed outgassing, subdued flaring, and asymmetric coma structure. 3I Atlas displayed all three traits. Its coma evolved slowly, its brightness curve rose reluctantly, and its dust production appeared patchy, as if fractures in the shell released volatiles in intermittent bursts. This behaviour drew immediate comparison to 1IA or Oumuamua, which also exhibited anomalous activity consistent with a hardened exterior. But unlike Oumuamua, which may have lacked volatile ices entirely near its surface, 3I Atlas clearly possessed active sublimation. It was a comet, an icy body from another system, yet one altered by deep time. The next clue came from colour data. Though limited by the proximity to the Sun, measurements hinted at a slightly bluish tint in the coma, implying a composition enriched in dust grains that scatter light more efficiently at shorter wavelengths. Some researchers suggested the presence of fine-grained silicates or carbon-rich particles. Such materials are common in young planetary systems, especially in regions near ice lines where comets tend to form. This raised one of the most compelling possibilities 3I Atlas may have originated in the outer disk of a star undergoing early planet formation. In those environments, comets are forged from the interplay of frost dust and volatile gases. Ices condense around silicate cores. Carbon compounds form long chains. Surface layers accumulate organics produced by ultraviolet radiation from the young star. When giant planets emerge and migrate, they destabilize outer reservoirs, flinging comets outward, some into distant outer orbits, and others entirely out of the system. 3I Atlas may be one such ejected remnant. Another clue came from the comet's dust-to-gas ratio. Preliminary modelling of its coma pattern suggested a dust-rich composition. Dusty comets tend to originate in regions of a protoplanetary disk, with abundant solid material places where planetesimals grow rapidly, and collisional grinding creates fine particles. If true, this would imply that the star system that birthed 3I Atlas once harboured active planet formation. But dust-rich comets also tend to fracture easily. The faint traveller showed signs of structural vulnerability. Its tail appeared segmented. The coma occasionally displayed small transient enhancements, possible microfragmentation events. These may have been caused by internal stresses built over eons in interstellar space. Without the cyclical heating and cooling experienced by solar system comets, interstellar objects accumulate stresses from cosmic rays, thermal gradients, and micrometeoroid impacts without periodic relief. When they finally encounter the intense heating of a star, those stresses release unpredictably. This could explain why the comet's brightness fluctuated irregularly. It could also account for the peculiar shape of its dust tail, at times curling, as if driven by jets erupting from localized fractures. The sun's radiation reshaped the object, rapidly revealing weaknesses etched into it during its lonely journey. Then there is the question of exotic chemistry. Although direct spectroscopic data on 3I Atlas was extremely limited due to its faintness and the difficulty of observing near the Sun, the behaviour of its sublimation hinted at the presence of compounds uncommon in typical solar system comets. Some researchers speculated that the object may have harboured supervolatile ices such as nitrogen or carbon monoxide in higher concentrations. These ices sublimate at far lower temperatures and could have influenced the comet's early evolution, possibly causing it to lose much of its near-surface material during earlier interstellar encounters with other stars. If 3I Atlas possessed such exotic ices, it may resemble objects like Triton or Pluto more than typical comets. Yet its activity near the Sun did not fully match that model. The muted outgassing instead pointed toward depleted surface layers, a sign of a long transformative past. All these clues, delayed sublimation, dust-rich emission, hardened crust irregular activity painted a picture of a body both familiar and alien. Familiar in that it reflected known cometary behaviour. Alien in that it reflected conditions shaped by a different star, a different disk, a different epoch of formation. The final clue is perhaps the most philosophical time. An interstellar comet survives not because it is intact, but because it adapts. Over unimaginable distances and durations, its materials evolve. The object becomes both less volatile and more resilient. It becomes colder, darker, harder. Its chemistry shifts subtly until it no longer reflects the signature of any specific star, but instead carries the imprint of the interstellar medium itself. 3i Atlas may be an archive of cosmic history storing within its dust and ices the memory of a molecular cloud that collapsed billions of years ago to birth a star now lost to anonymity. Its composition is not merely exotic, it is ancient. It represents a kind of deep-time geology, a frozen witness to chemical processes older than the solar system, older than the Earth, older than everything humanity recognizes as home. Thus, the realization dawned slowly but profoundly the faint object near the sun was not only a traveller, it was a relic. A message written in ice and dust carried across the galaxy and retrieved almost accidentally in the glare of a star. What it contained, what stories its chemistry tells remains largely hidden for the encounter, was brief, and the opportunity to study it was fleeting. But even the slight traces gleaned from its behaviour give humanity a window into something extraordinary, the ways in which matter itself evolves when it is allowed to drift freely among the stars. 3i Atlas was born beyond the sun in the cold outskirts of an alien world, and as it approached our star it revealed just enough of its strange ancient character to remind humanity that the galaxy is full of stories whose pages we can barely read. As the faint traveller drew nearer to the sun, its path narrowed into a geometry that seemed almost reckless, an orbit so steep that it grazed the edges of a domain defined by searing heat, crushing radiation, and gravitational tides capable of tearing apart even the strongest celestial bodies. Comets that follow such trajectories are called sun grazers, visitors that plunge dangerously close to the star's furnace, often ending their journeys in disintegration. But 3i Atlas was not a native sun grazer. It had not evolved over repeated solar encounters. It was an interstellar wanderer brushing a star for the first time in its long existence. This made its solar grazing path something far more dramatic, a confrontation between alien ice and stellar fire, a meeting billions of years in the making. The comet's perihelion approached with quiet inevitability. As it fell inward, the sun's radiation increased, exponentially pouring energy into the nucleus. What had been a cold, dormant shard of interstellar debris became an active body, awakening painfully as its surface absorbed thermal stress. The once dark shell, hardened by eons of cosmic irradiation, began to crack. Fissures opened. Subsurface volatiles stirred. Gases trapped since the dawn of another star system started to escape. This process reshaped the object in ways that were unexpected and to some degree contradictory. The most striking behaviour was the comet's asymmetric coma. Instead of expanding uniformly around the nucleus, the gas and dust appeared to be emitted preferentially from certain regions, forming plumes that curved strangely in the sun's fierce light. This curvature reflected the push of radiation pressure, yet it also hinted at underlying structural irregularities. Perhaps the nucleus possessed deep channels carved during its formation. Perhaps impacts from interstellar dust had weakened specific zones. Perhaps internal veins of super-volatile ice erupted in jets as the sun's heat reached them. Each possibility suggested a different origin story, but all pointed toward the same truth: the comet was being rewritten by its encounter with the sun. As the object descended into the inner heliosphere, it crossed a region where thermal gradients become extreme. Temperatures can shift by hundreds of degrees across a comet's surface in hours. Dust grains fracture, organic compounds melt and refreeze, internal pressures rise. In solar system comets that evolve over repeated cycles, these stresses are moderated by experience. Successive perihelion passages strip away weak materials and stabilize the structure. But an interstellar comet has no such evolutionary history. Its first star encounter may also be its last. 3i Atlas's behavior reflected this fragility. Its brightening remained modest, yet its morphology shifted rapidly. The tail lengthened abruptly, then split into separate filaments. The nucleus brightness fluctuated irregularly, suggesting rotational instability or localized outbursts. For a moment it appeared as though the object might fragment an interstellar visitor, unravelling under the sun's unrelenting glare. Such fragmentation would not have been surprising. Sun-grazing comets with native origins frequently disintegrate near the sun. The tidal forces alone can be catastrophic for loosely bound aggregates. Add the violence of solar radiation and survival becomes improbable. For 3I Atlas, the danger was compounded by its likely internal structure, a body shaped by cold chemistry over immense stretches of time, possibly porous, possibly layered, possibly riddled with stress fractures, accumulated over its interstellar journey. What made the situation even more precarious was the object's low initial brightness. Faint comets often indicate small nuclei objects only tens or hundreds of meters across. Such bodies are especially vulnerable to tidal and thermal disruption. And yet, despite the signs of stress, the comet remained coherent during its approach. It did not vanish. It did not explode into dust. It persisted thin and tenuous, threading the outer boundary of the solar firestorm. There is poetry in such endurance. The comet's sunward passage revealed the exquisite tension between fragility and resilience. The sun blistered its surface, yet the nucleus held. Radiation sculpted its dust, yet the object maintained its trajectory. Sublimation carved away material, yet something at its core remained intact enough for astronomers to track. This survival, however temporary, offered a rare glimpse into the behaviour of interstellar bodies. Encountering a star for the first time, some scientists wondered whether the object's material composition contributed to its surprising coherence. A nucleus with a higher proportion of refractory materials, silicates, carbonaceous compounds, or organics resistant to thermal decay could withstand solar heating better than one dominated by volatile ices. Alternatively, a heavily irradiated crust might have formed a protective shell, delaying catastrophic fragmentation until after perihelion. Others speculated that its small size may have been a protective factor. A larger, more complex body might have experienced uneven thermal expansion, leading to explosive breakup. A smaller nucleus uniformly heated might survive longer, simply because it lacks the internal stresses that destroy larger comets near the sun. Whatever the case, 3I Atlas's solar grazing trajectory was a rare natural experiment. It allowed humanity to witness how an interstellar body responds to stellar radiation, far more intense than anything it would normally encounter. Stars in the galaxy vary in brightness, but the sun by chance became the first star to bathe this ancient traveller in such overwhelming heat since its ejection from its home system. The encounter revealed phenomena that scientists could only theorize about before. The slow asymmetric coma growth, the irregular tail segmentation, the faint flickering brightening, the possible erosion of an ancient crust, the potential exposure of interior material unchanged for billions of years. These changes did not merely reshape the comet, they redefined it. Every moment near the sun transformed its chemistry. Every sublimating molecule altered its structure. Every dust grain carried away a piece of a history that began in another star's protoplanetary disk. And by the time 3I Atlas swung away from the sun, fading, dimming, drifting once more into cold space, it was no longer the same body that entered the heliosphere. In a sense, the sun and the comet had exchanged something. The star had taken fragments of an alien world, and the comet had left behind a trail of material that human instruments could analyze, however faintly. The encounter became a conversation across cosmic scales, an exchange between the oldest form of matter and the most luminous object in our sky. But the deeper significance lay not in what was lost, but in what survived. Despite the violence of its solar passage, despite the thermal onslaught and tidal strain, despite the perilous geometry of its orbit, the interstellar visitor endured long enough to be seen. A fragile shard from the dark between stars dared to approach the sun, brushed its fire, and lived through the encounter, leaving scientists with observations that would challenge assumptions and inspire new questions. Its trajectory near the sun was not merely a path. It was a revelation, one that made the mystery of 3I Atlas even deeper, and the need for further study all the more urgent. As 3I Atlas swept past the sun, its behaviour ceased to resemble the faint stability it had shown during its inbound approach. Now the object was shifting in ways that seemed almost restless, flaring and dimming irregularly, shedding dust in uneven pulses, twisting its tail into patterns that defied the smooth arcs typically seen in solar system comets. This unpredictable evolution drew the attention of astronomers. It suggested that the interstellar visitor was undergoing structural and thermal processes far more complex than the simple sublimation curves that define most cometary behaviour. The light curve, the record of its changing brightness, became the central key to this strange transformation. In ordinary comets, the light curve brightest smoothly as the comet approaches the Sun and dims symmetrically as it retreats. This symmetry reflects the geometry of illumination and the predictable release of volatiles. However, 3i Atlas produced a light curve that refused such order. It rose too slowly at first, then brightened abruptly in small bursts. It plateaued unexpectedly. It flickered as though responding to internal changes rather than solar geometry. And once the comet passed perihelion, it dimmed far more steeply than expected, as though portions of its nucleus had disintegrated or its volatile reserves had rapidly collapsed. Each deviation implied a story embedded in the object's interior. The slow initial brightening matched expectations of a heavily irradiated crust, one hardened by immense spans of interstellar travel. Such outer layers resist sublimation, shielding deeper ices from immediate exposure. But once cracks formed and subsurface reservoirs began venting, the brightness would rise in sudden surges consistent with the small flares recorded near the time of closest solar approach. These flares hint at thermal pockets, rupturing, releasing jets of gas and dust in directional bursts. Such outbursts can be diagnostic. They reveal the internal stratigraphy of a comet, layers of ice dust, organics, fractures and voids. In 3i Atlas, the intermittent nature of the flares suggested a highly heterogeneous internal architecture. Rather than a uniform mixture, the nucleus might have included pockets of volatile-rich material trapped between stronger sections of refractory crust. Its history of cosmic irradiation may have carved uneven internal channels. Micrometeoroid impacts accumulated over millions of years might have created weak zones ready to rupture, and each rupture leaves a signature in the light curve. Analysis of the brightness pattern revealed at least 3 such events, minor compared to major cometary outbursts, but significant for an object of this size. The timing of these events corresponded to changes in the shape of the dust tail. After each brightness jump, the tail would kink slightly, forming gentle curvature variations or faint secondary plumes. These patterns suggested that dust released in each burst possessed different grain sizes and velocities, implying compositional layering within the nucleus. The tail itself told an even deeper story. In typical comets, dust tails spread smoothly as radiation pressure sweeps particles away from the Sun. In 3i Atlas, the tail appeared segmented during keyframes, suggesting disruptions, not steady dust release, but episodic bursts. Such segmentation might be caused by rotational modulation, in which jets activate only when specific surface regions face the Sun. But given the object's interstellar origin and its unfamiliar structure, alternative explanations emerged. One hypothesis suggested that sublimation was occurring beneath the crust-building pressure until materials vented explosively. These micro-explosions could produce discrete dust clouds that drifted behind the comet in separated layers. Another possibility was fragmentation, small pieces breaking off and sublimating in sequence. Such fragmentation could produce faint debris trails, each corresponding to a separate event in the light curve. Observations hinted at small transient enhancements in brightness along the tail, perhaps fragments too small to survive long but large enough to add structure. Because the comet was observed against the Sun, the tail patterns were difficult to interpret with precision. Still, the persistence of segmentation indicated that the object was undergoing rapid evolution, its structure weakening under intense thermal stress. Even after perihelion, as 3i Atlas moved away from the Sun and back into darker, quieter regions of space, the light curve failed to return to predictable form. Instead, it decayed rapidly, as though the nucleus could no longer sustain steady sublimation. This suggested either that the volatile supply had been drastically reduced, or that significant structural damage had occurred, cracks, fractures, or partial disintegration that altered how the comet shed materials. In solar system comets, such behavior often marks the onset of fragmentation. Even if the nucleus remains gravitationally bound, internal cohesion may be compromised. For an interstellar comet, one weakened by billions of years of exposure to cosmic rays, such disruptions may be even more pronounced. The complexities of the light curve also hinted at irregular rotation. A rotating nucleus can exhibit periodic brightness variations as active regions come into and out of sunlight. But in the case of 3i Atlas, the light curve lacked clear periodicity. Instead of regular oscillations, it showed stochastic variation, erratic pulses with no repeating rhythm. This kind of behavior points to chaotic rotation, perhaps a tumbling motion, caused by uneven outgassing forces. Chaotic tumbling is consistent with a small irregularly shaped nucleus. Jets erupting from unexpected angles can impart torque, destabilizing the rotation. Once tumbling begins, it can amplify structural weaknesses, enhancing the risk of disintegration. Such rotational instability may also explain the difficulty in modelling the comet's coma shape, which appeared asymmetric and inconsistent across observational intervals. Despite the difficulties imposed by the sun's glare, analysts extracted from the light curve a portrait of a fragile evolving interstellar fragment, one that experienced a series of thermal, mechanical, and rotational stresses as it faced a star's heat for the first time in untold ages. The light curve thus became not merely a plot of brightness but a chronicle of transformation. Each sudden rise marked a fracture. Each plateau hinted at exhaustion. Each sharp dimming whispered of collapse. Together these features shaped a story of an ancient object encountering a star's fire with a mixture of resilience and instability. The comet's fading luminosity after perihelion, combined with the increasing irregularity of its dust tail, led many astronomers to suspect that it had lost significant mass. Some fragments may have detached entirely, others may have melted away. The nucleus that emerged after solar encounter was almost certainly smaller, structurally different, and chemically altered from the one that entered. But the most revealing aspect of the light curve is what it suggests about interstellar comet populations. If 3I Atlas is representative of such bodies, then interstellar objects may arrive in many states of preservation, some nearly intact like Borisov, others deeply altered by time like 3I, others perhaps fragmenting before detection. The galaxy's debris field may be more dynamic than once believed, and so the light curve of 3I Atlas stands as a fragile but deeply telling record, a set of flickering signals that reveal the strain, the awakening, the partial collapse, and the survival of an alien shard of cosmic history, illuminated briefly by the sun before fading once again into the silent cold. The deeper scientists probed into the behavior of 3I Atlas, the more they realized that its passage near the sun was not merely unusual, it was extreme in a way that pressed the limits of existing cometary physics. Many comets brighten, fracture, and reshape as they approach a star. But the changes observed in 3I Atlas, though faint and difficult to interpret against the solar glare, hinted at physical processes that stretched or contradicted long-held assumptions about the structural integrity and thermal response of ancient icy bodies. The comet's behavior did not simply challenge prediction, it defied the very models used to simulate sublimation fragmentation and internal heat flow. At the heart of this deepening mystery was the way 3I Atlas responded to solar heating. Cometary physics predicts that as a nucleus draws closer to the sun, the sublimation rate increases exponentially. Differing regions of the nucleus respond at different rates, but the underlying pattern remains broadly consistent. More heat produces stronger outgassing, which in turn sculpts tails and comae in predictable ways. But 3I Atlas exhibited something different, a disjointed, almost spasmodic sublimation pattern that failed to align with its thermal environment. This discrepancy grew more dramatic near perihelion. At a distance where most comets erupt into activity shedding dust in torrents, 3I Atlas displayed only modest brightening, yet paradoxically its structure appeared to be under severe distress. Subtle distortions in the coma indicated internal stress buildups, while abrupt shifts in the tail geometry suggested rapid release events. It was as though the comet were undergoing invisible structural transformations without producing the luminous signals that normally accompany such upheaval. This contradiction became one of the section's central puzzles: intense internal change paired with muted external expression. Even more puzzling was the possibility that the comet's nucleus was reshaping itself in ways that seemed at times incompatible with its survival. Normally, thermal stress and outgassing forces would either drive a comet into full fragmentation or stabilize its shedding patterns. But 3I Atlas hovered in a strange middle state, distorted enough to indicate mechanical strain, yet coherent enough to persist. This unstable equilibrium suggested a nucleus unlike those known in the solar system. One hypothesis emerged: the comet may have possessed a layered internal structure, with alternating sections of volatile pore-hardened crust and volatile-rich veins. Such heterogeneity could produce uneven outgassing forces that tugged the nucleus in conflicting directions. Under certain conditions, these forces might even stabilize each other, preventing immediate breakup, while still causing severe internal strain. But models of thermal propagation struggled to reconcile this with the muted brightness. The energy absorbed by the surface should have produced more visible activity. Another possible explanation was that 3I Atlas had an unusually compact nucleus, perhaps denser than that of typical comets. If the body contained more refractory materials paradoxical for a comet, it might withstand heating without erupting violently. Yet even minor sublimation would then produce disproportionate torque, potentially setting the comet tumbling unpredictably. Its irregular light curve aligned with this idea. But again, extreme density contradicts expectations for interstellar objects, which are generally assumed to be porous and fragile after billions of years adrift. The escalation continued when researchers simulated the object's structural evolution during its solar encounter. Many models predicted disintegration, yet observations showed survival partial weakened but real. This survival contradicted the majority of thermal fracture simulations for cometary bodies of comparable size and composition. Something about the nucleus, its internal strength, its binding chemistry or its thermal retention properties, did not match preconceived solar system analogues. Its trajectory added another layer of astonishment. The steep angle of its approach increased its thermal load far beyond that of ordinary comets. Rather than skimming gently across lines of solar heating, it plunged almost directly inward, accumulating an immense and rapid increase in energy. Such a path normally produces catastrophic disintegration, especially for small objects. Yet 3I Atlas maintained coherence long enough for post-perihelion observations, a fact that strained the limits of predictive models. In the days following perihelion, the mystery deepened. The comet's brightness declined far too rapidly. This steep decay suggested that the nucleus had suffered dramatic mass loss or structural compromise. But the absence of a large sudden outburst contradicted any single explosive event. Instead, the nucleus seemed to have shed mass gradually, or perhaps dissolved into a cloud of dust so fine that only sunlight scattering off the smallest particles remained visible. This behavior mirrored neither classic disintegration nor stable retreat. It represented a third category, unstable, fading a poorly understood regime in which a comet loses integrity too slowly to explode yet too quickly to behave predictably. Some astronomers posited that the object entered a transitional state between coherent nucleus and debris cloud. In this state, clusters of dust and ice remain gravitationally bound but fragile. The cluster acts like a porous, dissolving aggregate shedding material continuously. Such ghost nuclei have been suggested for certain faint comets, but 3I Atlas may be the first interstellar example. The idea raised unnerving implications. If interstellar comets commonly transition into such fragile clusters near stars, many might pass through other systems leaving no coherent nucleus behind, meaning countless such visitors could slip past detection entirely. The existence of 3I Atlas observed only because it crossed the sun's gaze then becomes a rare exception. The galaxy may be full of dissolving shards that never reveal themselves. Another troubling implication emerged: the object's faintness may not reflect small size alone. Instead, it may reflect intense surface processing from countless eons under cosmic radiation. The outer layers may have become carbonized, transforming into dark, refractory crust. Such layers would absorb heat differently, creating internal temperature gradients that standard models do not account for. Under this scenario, 3I Atlas might represent a class of interstellar bodies fundamentally different from typical solar system comets, not just older, but chemically evolved in alien ways. This realization pushed researchers toward a disquieting hypothesis. Interstellar comets may follow physical rules that diverge from those observed in the solar system, not because physics differs, but because time radiation and environmental history alter their behavior in ways our models rarely consider. The deeper the analyses went, the clearer it became 3I Atlas was not merely difficult to categorize. It exposed blind spots in comet science itself. It operated near the Sun with a combination of muted sublimation, structural instability, and non-standard tail evolution that forced researchers to confront how little is truly known about the evolution of icy bodies across galactic scales. And at the center of this expanding puzzle was a simple, unsettling tension. The comet behaved as though it was both stronger and weaker than expected. Stronger in its ability to survive the sun's fury, yet weaker in its light curve-tail behavior and post-perihelion decay. This paradox, simultaneous resilience and fragility reshaped the scientific dialogue. What forces preserved the nucleus against intense heating? What internal processes destabilized it so profoundly? What unseen physics controlled the dissolution of this interstellar relic? These questions form the mystery's new frontier, a deeper challenge overshadowing even the shock of its interstellar origin. For though the comet had passed the Sun, its behavior continued to contradict expectations, forcing astronomers to acknowledge a humbling truth. The laws governing such ancient objects may be universal, but the ways those laws manifest in matter, shaped by alien histories, remain beyond the horizon of certainty. 3I Atlas had not simply survived the Sun's fire, it had revealed how little is understood about the fragile ancient travellers that drift between the stars. Once the comet's interstellar trajectory was undeniable, once its erratic behaviour near the Sun challenged familiar comet physics, the scientific conversation turned toward a deeper realm of inquiry. The theories that might explain what 3I Atlas truly was, how it formed and how it endured the unimaginable journey between stars. These theories were not idle speculation. They emerged from the hard data, the delayed sublimation, the muted brightening, the abrupt post-perihelion fading, the segmented tail, the chaotic rotational behaviour, and above all, the object's billion-year odyssey through the interstellar medium. Each hypothesis aimed to reconcile these clues with known physics, pushing the boundaries of what scientists believed possible for celestial fragments shaped in alien environments. The first theory considered the comet as a primordial planetesimal, a relic forged during the earlier stages of a distant star's formation. In protoplanetary disks, icy bodies condense beyond the frost line, gathering dust ices and organic molecules into loosely bound aggregates. Such planetesimals frequently interact with growing planets. Gravitational scattering can fling them into distant orbits or eject them entirely from the system. If 3I Atlas originated in such a disk, its composition would reflect the chemistry of another star's nursery. Its hardened crust may represent billions of years of exposure to cosmic rays, while its volatile pockets, activated only when heated by the Sun, may trace the primordial chemistry of its home system. This theory aligns with its delayed outgassing and irregular light curve, but it raises a deeper point. 3I Atlas may preserve material that predates the solar system itself. In this view, every dust grain shed during its solar encounter is a piece of cosmic archaeology. His second theory emerged from the peculiarities of the comet's internal structure. Some researchers propose that 3I Atlas might be a fractured remnant of a larger parent body, perhaps once part of a moonlet or a protoplanet destroyed in a young violent system. In regions where giant planets migrate, gravitational instabilities can tear apart small bodies. Fragments are scattered in all directions, some inward toward the star, others outward toward interstellar space. If 3I Atlas was such a fragment, its irregular layered interior could represent a cross-section of a complex body containing materials formed at different depths. This hypothesis explains the comet's uneven outgassing patterns, its sporadic flares, its tail segmentation, and the thermal tensions observed near perihelion. A fragmented object would possess heterogeneous zones, some hard, some fragile, creating the patchwork sublimation behavior reflected in the data. A third theory considered the possibility of supervolatile enrichment, especially given the comet's modest brightening near the Sun. Some researchers hypothesized that 3I Atlas contained exotic ices, nitrogen, carbon, monoxide, methane, or even molecular hydrogen in certain forms embedded deep within the nucleus. Over billions of years in interstellar space, the more volatile layers near the surface would have escaped, while deeper reservoirs remained preserved. Upon approach to the Sun, these ices would sublimate irregularly, producing bursts of activity followed by abrupt declines. Such behavior mirrors what has been speculated for 1I Oumuamua, which may have been driven by outgassing of hydrogen or nitrogen rather than water vapor. The presence of supervolatile ices would also imply that 3I Atlas originated in the outermost regions of a cold, distant protoplanetary disk, perhaps analogous to the solar system's Kuiper belt or Oort cloud, but formed around a star with different temperature gradients or elemental abundances. A more exotic speculation proposed that the comet's crust may have undergone cosmic ray-induced polymerization. Over millions of years, high-energy particles in interstellar space can transform organic molecules into long-chain polymers or carbon-rich macromolecules. These materials darken the surface, reduce sublimation efficiency, and change thermal conductivity. Such an irradiated layer could act as a thermal insulator, delaying sublimation until the comet reached extreme proximity to the Sun, consistent with the delayed brightening that puzzled observers. This polymerized crust would be extremely fragile when heated, potentially explaining the object's abrupt fading and possible fragmentation after perihelion. It would also imply that interstellar comets evolve chemically in ways that solar system comets do, not shaped by environments where starlight is faint, but cosmic radiation is relentless. Another theoretical framework focused on thermal fracturing and rotational destabilization. The irregular pattern of brightness changes suggested that outgassing jets may have set the nucleus tumbling chaotically. In such a scenario, forces imparted by sublimation interact with the object's rotation to create feedback loops. Outgassing accelerates spin, alters sunlight exposure, altered exposure modifies outgassing. This can drive a small comet into a state of rotational stress sufficient to tear it apart, yet not instantaneously, creating a prolonged phase of instability. This theory explains the lack of periodicity in the light curve and the signs of internal strain without a single catastrophic event. If correct, 3I Atlas may represent a case study in rotational breakup, triggered during a first-ever close encounter with a star. More ambitious models considered the comet within the larger context of galactic dynamics. Some theorists suggested that 3I Atlas might have originated in a stellar nursery that has since dispersed, possibly near the outskirts of a young cluster. Such environments are chaotic with gravitational tides and stellar encounters that can eject debris at high velocities. If the comet was launched during this turbulent early phase, it may have spent hundreds of millions of years traversing the galactic disk, gathering the scars of radiation dust and temperature gradients. This scenario is supported by its unusual radiant, which does not match the typical flow of interstellar objects predicted by galactic models. Rather than aligning with the Sun's apex direction or known stellar streams, 3I Atlas appears to have approached from an unexpected vector, perhaps tracing a path shaped by long-forgotten stellar interactions. At the edge of more speculative theories lies the idea of false vacuum artifacts or quantum field relics, not in the sense of exotic matter, but in the sense of objects shaped by extreme environments early in the galaxy's history. Some researchers pondered whether 3I Atlas might include isotopic ratios that hint at unusual star formation events, perhaps a fragment of a disk enriched by a supernova or material processed in molecular clouds exposed to shock fronts or cosmic turbulence. These ideas remain untested, but the comet's behavior encourages curiosity about how different formation environments shape the evolution of icy bodies. Despite these varied theories, one truth cuts through them all. 3I Atlas challenges existing models because it is shaped by a history humanity has never directly witnessed. Its composition, structure, and physical behavior are not anomalies. They are products of environments far beyond our familiar solar system, and that realization forces scientists to expand their understanding of cometary physics from a local science to a galactic one. 3I Atlas is not merely an object, it is a lesson, a reminder that the galaxy is ancient, diverse, and full of frozen messengers carrying the chemical signatures of worlds and stars long vanished from memory. In studying it, humanity opens a window into the physics of other suns, other disks, other epochs. A window into the silent exchange of matter between star systems, carried on the backs of fragile drifting shards, like this one's shards that survive the journey only to reveal their secrets in the fleeting moments when they encounter a new sun. To understand an interstellar comet is to confront a scientific challenge that stretches beyond the limits of direct observation. 3I Atlas appeared near the sun, faint and distorted by glare, leaving behind only fragmented photometric trails and ambiguous morphological clues. No spacecraft flew past it. No spectrograph captured its chemistry in detail. No high-resolution images resolved its nucleus. What remained was puzzle-like, a sequence of faint points, a handful of dust profiles, and a trajectory carved through gravity alone. Yet from these narrow windows emerged an expansive effort, scientists around the world turning to laboratories and supercomputers to simulate the unseen physical processes shaping the comet's transformation. To reconstruct an object that cannot be examined, one must recreate its physics. And so scientists set about doing exactly that, simulating a body forged beyond the sun. The first step in understanding 3I Atlas lay in simulating the materials likely to compose an interstellar nucleus. Laboratories began replicating the conditions of deep interstellar space, vacuum chambers cooled to near absolute zero, ices layered with dust grains, organic molecules irradiated with ultraviolet light and cosmic ray analogues. These experiments attempt to mimic the chemical weathering experienced by a comet adrift for millions or billions of years. One result stood out immediately: prolonged radiation transforms simple organics into dark, polymer-rich crusts. These crusts resist sublimation fracture under thermal stress and act as insulating shells, preserving deeper volatile reservoirs. When heated rapidly, as would occur during a first encounter with a star, the crust cracks unpredictably, releasing jets that match the flaring behavior recorded in 3I Atlas's light curve. This correspondence between experiment and observation strengthened the hypothesis that 3I Atlas possessed a hardened, irradiated shell, a kind of cosmic armor forged in deep space, but laboratory simulations alone were insufficient. The true drama unfolded not in slow-controlled conditions, but in the rapid furnace-like rise of temperature near the Sun, a phenomenon impossible to mimic fully on Earth. Supercomputers and the heat of a star. To study this transformation, researchers turned to computational models capable of simulating sublimation heat diffusion, tensile stress, rotational instability, and particle ejection. One class of models focused on heat transport within porous bodies. These simulations revealed how radiative heating penetrates fractured materials, sometimes in unexpected channel-like patterns. They demonstrated that a nucleus with heterogeneous composition, ice-rich veins trapped between layers of refractory dust would sublimate in bursts matching the episodic brightening observed in 3I Atlas. Another model class explored thermomechanical stress, showing how rapid temperature gradients near the Sun generate internal pressure waves that race through the nucleus. In weak zones, these forces produce cracks, sometimes tiny fissures, sometimes catastrophic fractures. For an object like 3I Atlas, long exposed to cosmic radiation, the interior may have been riddled with microfractures primed to expand under heat. Some simulations suggested that the nucleus could enter a state of progressive disassembly, where no single event destroys it, but steady, uneven erosion destabilizes the entire structure. This behavior resembled the comet's rapid post-perihelion fading, a signature of a nucleus transitioning toward dust, modeling the interplay of jets and rotation. Another set of simulations focused on gas jets and rotational dynamics. These models demonstrated that asymmetric jets could torque a small nucleus into chaotic rotation. For an irregular body, this tumbling motion would change sunlight exposure rapidly, creating alternating cycles of heating and cooling across the surface. Such cycles could amplify thermal stress and increase the likelihood of fragmentation. Simulations of irregularly shaped nuclei showed behavior eerily reminiscent of 3I Atlas's light curve, non-periodic flaring, sudden dimming, and the absence of stable rotational rhythms. This chaotic rotation model also explained the segmented dust tail. Each burst of activity would release grains at different angles and speeds, creating separate layers of dust that drifted behind the comet, like pages torn unevenly from a burning manuscript. Dust physics reconstructing the tail. To make sense of the tail's changing patterns, scientists turned to particle flow simulations under solar radiation pressure. These models showed that a dust tail is not a simple plume, but a complex dynamic arc shaped by the interplay of grain size, solar wind, and radiation pressure. Fine grains create diffuse streaks. Larger grains form sharper filaments. If the comet's nucleus released grains in bursts each with distinct composition or size, its tail would appear segmented exactly as recorded in the imagery near perihelion. Such segmentation is unusual in solar system comets, which often release dust in smoother distributions. But simulations showed that an interstellar comet with its layered internal chemistry could release dust in discrete chemical slices, each reflecting a different evolutionary era of the nucleus. Chemistry under alien stars. Laboratories also simulated exotic ice behavior, including nitrogen, methane, and carbon monoxide ices that sublimate at temperatures far below water ice. These ices are abundant in the outer regions of protoplanetary disks, but rare near the Sun. If 3I Atlas contained such supervolatiles deep within its interior, their sublimation would produce erratic jets and structural weakening, not bright outgassing typical of water or carbon dioxide. This aligned with the comet's peculiar profile, structural deformation without dramatic brightness increase. Chemical simulations further suggested that interstellar radiation may alter isotopic ratios or create crusts enriched in complex organics, a possibility consistent with the comet's muted glow and unusual tail features. Simulating galactic time. The final class of models extended beyond the nucleus to the galaxy itself. Researchers simulated how interstellar comets wander, how gravitational tides from passing stars nudge them, how collisions with dust erode them, how cosmic radiation modifies their surfaces, how they become darker, harder, and more brittle over time. These simulations portrayed interstellar comets as ancient survivors fragments shaped not by a single star, but by time itself. By the time they encounter a new star, they may be chemically transformed, structurally weakened and evolutionarily distinct from any comet born in that new star's light. 3I Atlas fit this simulated profile almost exactly. Its faintness, its delayed activity, its irregular tail, its chaotic rotation, its rapid post-perihelion decay all matched the predicted behavior of a body aged beyond anything found in the solar system. The new frontier. Simulation thus became the only bridge between observation and understanding. Without direct imaging or spectral analysis, scientists relied on physical models to extract meaning from faint patterns of movement and brightness. And with each simulation, a clearer picture emerged. 3I Atlas was not just an interstellar object. It was an interstellar survivor, a body shaped by conditions beyond Earth's laboratories, beyond familiar starlight, beyond classical comet models. Simulations and laboratory experiments revealed that the comet's unusual behavior was not anomalous. It was instructive. It taught researchers that interstellar comets may be more diverse, more fragile, more chemically complex, and more structurally evolved than anyone had imagined. In this way, 3I Atlas became a prototype, not simply an isolated visitor, but the first member of a larger unseen population that science must now learn to understand not through direct measurement, but through the patient, meticulous craft of simulation. The discovery of 3I Atlas was never planned. It was not the target of a coordinated search nor the goal of a multi-million-dollar mission. It was a coincidence, a byproduct of technology built for an entirely different purpose, watching the sun. Yet once the interstellar nature of the object became clear, NASA and the broader astronomical community found themselves confronting an unexpected truth. If a faint alien shard could appear in the very region of the sky where detection is hardest lost in glare, overwhelmed by solar fire, then how many interstellar objects had slipped past unnoticed? And more importantly, how should humanity prepare for the next one? In this sense, the detection of 3I Atlas became more than a scientific curiosity. It became a catalyst. It forced space agencies to reconsider how they search for interstellar visitors. It highlighted weaknesses in existing survey systems, and it illuminated the need for new protocols instruments and observational strategies designed not merely for asteroids and comets of solar origin, but for wanderers arriving from the deep galactic dark. NASA's response unfolded quietly at first through teams tasked with analyzing the detection pipeline data handling and imaging cadence of solar observatories. But soon the effort expanded into something more structured and forward-looking, refining solar data pipelines. The first lesson learned was that instruments pointed at the sun are unexpected but powerful detectors of inbound interstellar objects. Coronagraphs and heliospheric images routinely capture faint, fast-moving points that would otherwise escape detection. Yet these instruments operate with data pipelines optimized for solar physics, not moving object tracking. Analysts began developing software capable of automatically flagging non-radial motion objects drifting across the solar wind instead of with it. 3I Atlas had been noticed because of human attention, but future detections could not rely on happenstance. New algorithms were trained to distinguish between comets, cosmic rays, diffraction artifacts, and high-energy particle hits. These tools began scanning decades of archival data, as well searching for faint anomalies previously overlooked. Some of these archival searches revealed additional unclassified moving objects, most likely solar system comets, but a few with mysterious, insufficiently constrained trajectories that warranted deeper study. The sun, it turned out, might already have hidden an entire archive of such wanderers in plain sight. Integrating Atlas and solar observatories, NASA also strengthened the connection between solar observatories and sky surveys such as the Asteroid Terrestrial Impact Last Alert System ATLAS. In the case of 3I Atlas, Atlas provided critical pre-discovery imaging that confirmed the object's interstellar nature. But this synergy had never been formalized. Now it has become a strategy. New protocols ensure that, when solar imagers detect an anomalous moving target, Atlas and similar surveys receive rapid coordinate updates. Ground-based telescopes can be redirected immediately to search for pre- or post-perihelion detections. Orbital calculations incorporate solar imaging metadata in real time. This integrated approach dramatically improves the ability to identify interstellar trajectories before an object disappears back into the dark, preparing for future interstellar objects. The discovery of 1I, Oumuamua, and 2I, Borisov had already pushed NASA toward interstellar preparedness, but 3I Atlas sharpened the urgency. NASA's Planetary Defense Coordination Office expanded its mandate to include the early identification of interstellar objects not because they pose a threat, but because each represents a rare scientific opportunity. 3I Atlas was especially sobering. It showed that interstellar visitors can pass so close to the Sun that they remain nearly invisible to traditional sky surveys. To address this, NASA began examining 3 major lines of development. 1. Enhanced wide-field surveys. Projects like the Vera C. Rubin Observatory LSST promise to revolutionize detection sensitivity for faint, fast-moving objects. NASA has now aligned its interstellar detection goals with LSST's capabilities, developing software pipelines specifically designed to identify hyperbolic trajectories early. 2. Dedicated space-based comet trackers. There is growing interest in placing small telescopes at L1 or L5 to monitor the Sun's vicinity for non-solar moving objects. These missions, designed from the start for dual-purpose detection, would incorporate both solar instruments and wide-field object tracking. 3I Atlas revealed that such hybrid instruments could catch interstellar comets when they are brightest near perihelion, even when Earth-based telescopes cannot. 3. Interstellar intercept strategies. Perhaps the boldest effort involves missions meant not merely to observe interstellar objects, but to reach them. Plans for the Interstellar Probe Interceptor. A mission designed to launch rapidly toward newly discovered interstellar visitors were already in conceptual development after Oumuamua. But 3I Atlas intensified momentum behind these proposals, highlighting the need for faster identification timelines. If humanity hopes to intercept such an object, the window for launch must open within weeks, not years of discovery. 3I Atlas passed before such a mission existed, but its detection helped pave the way for ones that may be launched in the near future. Understanding a galactic population. The implications of 3I Atlas stretch beyond detection logistics. The comet demonstrated that interstellar objects may not merely be occasional anomalies, but part of a larger galactic ecosystem. The object's faintness suggests a hidden population far more numerous than once thought, most too dark, too small, or too close to the Sun to be seen. NASA scientists began modelling interstellar object populations with far higher densities than earlier estimates. In these newer models, tens of millions of interstellar fragments may pass through the solar system each year. Most are microscopic or meter-sized, invisible to telescopes. A handful may be tens or hundreds of meters across, detectable only under special conditions. 3I Atlas was one of the rare few large enough, active enough, and well-positioned enough to be noticed. Why NASA cared? Despite its faintness and fleeting visibility, 3I Atlas represented an invaluable scientific opportunity. Each interstellar comet carries chemical memories of its birthplace, a frozen history of a star and a world long vanished. The mere act of detecting such an object provides insight into the diversity of planetary systems, the frequency of volatile rich bodies, the processes that eject comets into interstellar space, the long-term evolution of icy bodies beyond stellar influence. NASA tracked 3I Atlas because it recognized that interstellar objects are among the oldest and most pristine artifacts available to science. They are untouched by the Sun until their arrival. They are messages from stars we may never reach. Every such object detected expands humanity's understanding of the galaxy, a catalyst for a new era. In the aftermath of 3I Atlas, NASA's interstellar preparedness has become more mature, more systematic, and more urgent. The faint traveller served as a reminder that even in the era of advanced observatories, cosmic visitors can still appear unannounced, slipping through regions of the sky where humanity is nearly blind. 3I Atlas did not merely enrich our understanding of interstellar matter, it reshaped the way science prepares to meet such wanderers, and as the Sun's stray visitor faded back into the vast black between stars, it left behind a legacy far larger than its dust, the knowledge that the universe is still filled with secrets, and that Earth must be ready when the next one arrives. Long after 3 Atlas had retreated from the Sun's furnace and slipped back into the cool twilight of the outer solar system, dimming rapidly, dissolving into obscurity, scientists continued to study the thin traces it left behind. Every fragment of data, every faint photometric pulse, Every distorted dust plume offered a fragile key to something far larger, the ancient environments where interstellar comets are born. For while 3i Atlas revealed little about its own star system, directly, its behaviour illuminated patterns common to the processes that create and shape worlds. In the end, the comet became not a singular curiosity, but a window into cosmic origins, into the chemistry, physics and violence of the galaxy's stellar nurseries, a messenger from the birthplaces of stars. Interstellar comets originate in regions where planets are forming a chaotic realm of gas dust and radiation, where gravity sculpts small bodies from cosmic rubble. The unusual characteristics of 3i Atlas revealed that its birthplace was likely a young active protoplanetary disk, one shaped by distinctive conditions: strong ultraviolet radiation, abundant carbon-rich grains, varied volatile compounds, rapid mixing of dust and ice. Such environments are common around sun-like stars, but their specific chemistry can vary drastically. Because 3i Atlas carried a hardened, irradiated crust combined with deep, volatile reserves, its traits pointed toward formation beyond the frost line of a disk, influenced by an energetic central star, perhaps one more active or more massive than the Sun during its youth. This made the comet a rare sample of alien planetary chemistry. Not through physical capture, but through observation of how its materials behaved under solar heating. The slow brightening irregular jets and muted activity implied that the comet's volatile composition had been shielded beneath a processed surface layer. This layer did not arise near the Sun, but long before within the molecular cloud that preceded its original star. Their grains coated in ices condensed and interacted with cosmic radiation, forming organic compounds fundamental to prebiotic chemistry. The interstellar medium is not barren. It is the birthplace of molecules essential for life-complex organics, carbon chains and frozen gases that may seed young planetary disks. 3i Atlas was built from that cosmic recipe. Echoes of stellar nurseries. The comet's behaviour near the Sun also offered indirect evidence of the environment in which it lived during the earliest part of its history. If 3i Atlas contained supervolatile ices such as carbon monoxide or nitrogen, its birthplace must have included areas of intense cold regions, beyond the reach of direct stellar radiation, where temperatures plunge low enough for such ices to form. This corresponds to areas of a disk analogous to the Kuiper belt or scattered disk around the Sun, but perhaps denser, more turbulent and more active. If its crust contained complex organics created by ultraviolet processing, then its birth environment must have been exposed to strong stellar activity. This suggests that the comet's star may have experienced high flare rates, strong magnetic cycles, or a period of intense accretion, all typical of young solar analogues. If the nucleus contained insulating dust-rich layers, then its protoplanetary disk may have undergone strong radial mixing, bringing material from the inner and outer disk into sustained contact. Thus, 3i Atlas became a reflector of the past. Its chemistry, though not directly measured, encoded environmental signatures of a young star that once burned far away, perhaps across the spiral arm of the Milky Way. Ejection from a growing planetary system. To become interstellar, the comet must have been expelled. This required a dramatic event, one powerful enough to fling a small icy body past escape velocity. 3 mechanisms dominate the ejection theories. Giant planet migration. As massive planets move through their disks, they scatter surrounding planetesimals. Some are sent inward, others outward, a small fraction escape entirely. 3i Atlas may have been part of this outward scattering. Binary star interactions. If the comet's home star was part of a binary system, gravitational interactions could have ejected debris efficiently. Many stars in the galaxy form in binaries, making this a strong possibility. Cluster dispersal. If the object formed in a dense stellar cluster, close encounters with neighbouring stars could have launched it into interstellar space. Each scenario paints a picture of violence with gravitational tides, reshaping young planetary systems and flinging debris across the galaxy. In such a scenario, 3i Atlas was not a rare exception. It was simply one among countless shards ejected during the early chaotic reshaping of stars and planets. Its survival over immense timescales despite deep space radiation, micrometeoroid impacts and cosmic heating speaks to the durability of these primordial remnants. A link between star systems, perhaps the most profound significance of 3i Atlas lies in what it implies about the galaxy-wide exchange of material. Interstellar comets are not isolated. They are part of a constant flow, slow, steady and ancient, of matter drifting between star systems. A single supernova shockwave can sweep through a molecular cloud, stirring up debris. Planet migration can eject millions of stray comets. Stellar winds and gravitational tides can reshape entire clusters, sending icy fragments drifting across the spiral arms. Thus, objects like 3I Atlas may act as interstellar couriers, not carrying life necessarily, but carrying chemical information recipes for organics, traces of isotopes, mixtures of dust and ice that can influence the composition of new systems. Some of these fragments may eventually be captured by young planetary disks. Others may collide with forming worlds. The galaxy becomes a crucible of shared materials, each star contributing to the chemistry of future generations. 3I Atlas was a witness to this grand exchange, a traveller from a star perhaps long extinguished, a messenger from a disk that once shimmered with heat and dust, a relic of the turbulent birth of worlds, a glimpse into the Milky Way's history. Ultimately, 3I Atlas's importance lies not in its brief visibility near the Sun, but in the way it forced scientists to rethink the cosmic environment that surrounds humanity. The comet demonstrated that interstellar objects may be vastly more common than once believed. The solar system is not isolated, but embedded in a dynamic galactic ecosystem. Small bodies exchange between systems over timescales that dwarf the age of human civilization. The chemistry of life's building blocks may move fluidly across star systems. It is a reminder that the molecules in comets, planets, and even living cells may share origins older and more distant than the Sun itself. Interstellar comets broaden humanity's understanding of what it means to belong to a star system. They blur the boundaries between ours and theirs. They reveal that the Milky Way is not a collection of isolated planetary nurseries, but a vast evolving network in which matter drifts, mixes cycles, and evolves. A final contribution, 3I Atlas did not leave behind fragments for spacecraft to collect. It did not linger long enough for spectrographs to dissect its composition. It did not blaze brilliantly like great comets of the past. But in its faintness, its fragility, and its motion, it revealed something deeper, a story of formation and ejection, of interstellar wandering and stellar encounter, of memories preserved in ice older than Earth. In the end, the comet became a lens one that allowed humanity to glimpse the galaxy's oldest stories through the brief passing of a dim ancient traveller. The mystery it illuminated was not only where it came from, but how connected all star systems truly are bound by the quiet, ceaseless exchange of drifting cosmic remnants forged at the dawn of time. For a brief moment in cosmic time, 3I Atlas occupied a place where its presence could be seen, a narrow window in which an ancient fragment drifting between the stars intersected with the light of the Sun and revealed itself through faint, trembling signals. And just as quickly it vanished. Its trajectory carried it outward, back through the heliosphere's thinning winds, past the orbits of the planets, and toward the vastness from which it came. But its departure did not mark an ending. It marked a beginning, an opening into questions far larger than the object itself. As the comet dimmed into invisibility, astronomers turned to the deeper meaning of its appearance. What does such a visitor represent? What does it teach us about the galaxy, about time, about matter, about the very act of being present in a universe where stars and worlds appear and fade like sparks? The story of 3I Atlas is not a story about a comet alone. It is a story about connection, about the quiet threads of material that weave through the Milky Way, tying distant star systems together in ways invisible until moments like this reveal the pattern. The comet's final recorded brightness showed a body in decline. Its tail had grown diffuse, its nucleus had weakened. The once coherent core seemed to dissolve, shedding fine particles that drifted behind it like ash. By the time it crossed beyond the reach of solar images, it resembled more a cloud than a solid traveller, a fading memory of its former self. Yet this dissolution was not a failure. It was transformation. The object had survived the sun's fire long enough to be witnessed. Whatever remained of it continued onward, carrying the memory of its long journey out into darkness once again. Its escape into the void mirrors the fate of many interstellar wanderers. Few remain intact after their encounters with stars. Most lose mass fracture, or gradually become ghost-like clusters of dust, bound only loosely by their own dwindling gravity. Over time they fade into the galactic background, indistinguishable from the countless particles of cosmic dust that trace the spiral arms. And yet their journeys matter, for they chart the long silent exchange of materials forged in a different stellar nurseries. What 3I Atlas leaves behind then is not a physical trail that can be followed, but a conceptual imprint, a reminder that the Milky Way is older, more intricate and more interconnected than any single star or planet can reveal. Each interstellar comet contains stories embedded in ice stories that began before Earth formed, before the sun ignited, before the elements in our bodies coalesced into solid form. For scientists, the comet's brief visit raised profound questions. How many such objects pass unseen? What chemical signatures do they carry? How much of Earth's own material history might include fragments originally forged around other stars? And what does it mean for a star system to be part of a galactic tapestry, in which matter flows continuously from one furnace of creation to another? These questions are not purely scientific. They are philosophical, touching on humanity's place in a universe shaped by exchange rather than isolation. 3i Atlas is a symbol of that exchange. It came not to illuminate the sky with brilliance, but to remind us that the universe is full of travellers' objects older than memory, bearing silent evidence of other worlds. The sun, with all its force and brilliance, could not erase that reminder. Against its overwhelming glare, the comet revealed itself faint but undeniable, and in doing so, it demonstrated that even in the most hostile observational environment, the universe finds ways to whisper its secrets when the right eyes are watching. The interstellar visitor passed, but the curiosity it awakened remains. It reminds us that the boundaries of the solar system are not walls but thresholds, that the cosmos is not empty but full of drifting messengers, that across billions of years and countless light years matter moves freely stirred by gravity and chance, connecting star to star in quiet arcs of motion. Humanity's task is simply to notice, to build instruments capable of deciphering these moments, to train minds capable of interpreting their meaning, and to remain open to the profound possibility that the galaxy is far more dynamic and interconnected than it appears from a single planet orbiting a single star. 3i Atlas has already left us, but the questions it raised, the mystery it deepened, and the perspective it offered linger in the silence it leaves behind. And in that silence there is a kind of beauty, the recognition that even the faintest of cosmic travellers can shift our understanding of the universe, not through spectacle, but through presence. And now, as the story ebbs, the pace softens. The comet has faded beyond the reach of telescopes, but its gentle traces continue to drift through thought like particles suspended in still air. The urgency of observation subsides, replaced by a slower, calmer wondering. The vast machinery of the sun quiets in the imagination, the heat and turbulence giving way to the quieter notion of distance of the long, cool expanses that cradle wandering fragments as they move between stars. In this softened space, the galaxy feels larger and more patient. Time stretches no longer measured in days of observation or moments of discovery, but in the quiet centuries through which such objects travel. The comet becomes less a scientific puzzle and more a companion, a reminder that even in the deep emptiness between suns there is motion, there is continuity, there is story. 3i Atlas drifts now into silence, becoming once again what it was for nearly all its existence, a small, lonely fragment wrapped in darkness, unhurried and unobserved. And yet, because it brushed the sun, because it crossed the narrow beam of human awareness, it is remembered, not brightly, not loudly, but gently, like a faint glow preserved in memory. So let the final image settle, a dim traveller moving outward, slowly cooling, slowly quieting, returning to the interstellar dark. Around it the stars turn with unending patience. Ahead the galaxy unfurls like a soft endless sea. And somewhere far from any sun the fragment continues its long journey unchanged in its solitude, yet forever part of our story now. Sweet dreams.